Okay? So much for the overall setup then. So now we're going to talk a bit more about the compiler itself. So here's a kind of overall picture of the way HsSyn as a whole works. So we talked about the driver pipeline, which is this bit that runs all these programs one at a time. The HsSyn internally is structured so that it has what we've started to call the HsSyn API. So this is meant to be a Haskell interface that allows a client application to say import GHC and then do essentially everything that GHC can do. So on top of this interface is GHCI, the interactive version of GHC. So GHC is only structured as several clients, all built on top of this same API. But in principle, this API is usable by other clients entirely. Right, so the interactive user interface GHCI is built on top of this. The -- make thing that goes off and runs and compiles multiple modules is built on top of this. And the GHC-M, which outputs dependencies, is also built on top of this same API. So this API is capable of dealing with compiling multiple modules, whole programs in other words, that consists of graphs of modules, directed indeed possibly cyclic graphs of modules. But we're not going to deal with this first. Then we're going to first of all look at what happens when you compile a single module, because I find that's a lot easier to get my head around. So I start to get some sort of anchor. So we're going to start at a sort of middle out version. Start with HsC main. So this is also in compiler main. HsC main is the module that deals with compiling a single Haskell module, steers the compilation of a single Haskell module, and that's where we're going to start, essentially probably for most of the rest of this morning, and then work down from there. And then after that, we'll work back up in this direction. Does that make sense? Just want to keep you oriented as to where we're going. So, backing up then to that slide we were looking at before about compiling one module. Here there are things you might. There's a little note here about some remarks about the coding guidelines we use when building the compiler, and we may come back to module dependencies. The compiler uses quite a lot of cyclic collections of modules. So module A depends on B, depends on C, depends on A. Why? It's typically because there's recursion among the data types, and GHC has a lot of data types, and so it's very difficult to keep the modules non-recursive. So when you're altering GHC particularly, it's helpful to know where these loops are and how they're crafted, rather than how to re-engineer them from scratch. And you'll find that documented in this link here. I don't think we'll go through it together, at least not to begin with. Instead, we're going to tackle compiling one module. So here is here's what happens when we compile a single Haskell module. So the commentary, I'm hoping that many of you can see this text on your own screens. There's some commentary here in words, but I'm here just at the moment, I'm going to look at the picture at the bottom. So the first thing that happens is we compile our now deliterated DCP process Haskell source file. We'll parse it into a big data type called HsSyn. And HsSyn is, I'll have more to say about later. Let's just keep the highlight for the moment. Then we apply the renamer, which deals with lexical scoping issues. And we'll come back to this too. Then the typechecker, which I've drawn big because there's quite a lot of code in the typechecker. And all of these three stages finish in HsSyn, but parameterized in a different way. So let me pause here then and back up to text. Right, so this text here describes these three stages, and describes how they all parameterize their HsSyn. Here's some remarks about the HsSyn type. Now the HsSyn type is really quite big. It represents the entire abstract syntax of Haskell in its full glory, down to the placement of parentheses and which character position every sub-expression begins and ends on. So it's got a lot of information. It doesn't yet contain comments, but very soon it will, right? Because it's going to be, if you wanted to make a client, remember that GHC API? If you want to make Haddock a client of the GHC API, the HsSyn type had better retain all the Haddockized comments that you put in. So very soon it will too. So this is a big data type. There's a spelling mistake, something you can fix. I counted 52 data types in HsSyn, and some of them have lots of constructors. So HsExpert has 40 constructors. So this is a very big description of the whole language. It does mean that the reason for keeping it in this form for such a long time is that all the error messages come out in a form that's comprehensible to programmers, because they see what they wrote, not some desugared version. Now, each of these, gives you a good reason about why you might have mutual recursion. So here are a list of all the modules in HsSyn, which deal with different parts of this data type. So there's data types for patterns, data types for literals, data types for expressions, for declarations, for import clauses, for bindings, and so forth. So these are spread out all over these 10 or so modules in HsSyn, and that's why the modules are mutually recursive. Okay, right. And each of these modules typically contains the pretty printer for the data types declared in that module, but really not much else. There's one module though, HsUtils, has essentially no data types in it, but quite a lot of utility functions that are helpful for building fragments of HsSyn or for crawling over fragments of HsSyn. And finally, there's one root module at the top, which is just called HsSyn, and that exports everything. Right? So typically, you'll see other modules in the compiler just importing the module HsSyn, because you get access to all of this stuff that way. Okay? Now, I want to say a few things about a few peculiarities about this very big data type that will trip you up if you don't know what they're there for. So, to a first approximation, HsSyn is pretty straightforward. Every production in the BNF for the language gets a constructor in the HsSyn type. So that's the right down to parentheses as well. But there are quite a lot of things that if you look at, you think that doesn't look like something that appeared in the BNF. And so I tried to list the ones that I could at least think of. If you find any others, please add them here, and you can put, oh, I came across this constructor, it didn't seem to be, in the abstract syntax, it didn't seem to be covered above, what is it? So just add to this bullet list. The ones that I thought of were these. The first thing to say is that the, actually before I do that, let me just tell you about this parameterization, because then it'll make more sense. So I remarked that the parser produces an HsSyn parameterized by rudder name. So what's the type parameter? The type parameter for HsSyn is the type of binding and bound occurrences of variables. Right? So when you write X in your source code, that's going to be one of these type parameters for HsSyn. And after the parser produces HsSyn parameterized by rudder names, and you can think of, to a first approximation, think of a rudder name as just a string. That's the string the programmer wrote. Okay? Then the renamer gets hold of it, and it transforms the rudder name HsSyn into name HsSyn. And you can think of name, to first approximation, as a string plus a unique. Right? And the unique number is not just for fast comparison, it also distinguishes two names, two variables in the source text that have the same string. They're both F, but they're actually different Fs, right? We know about that, it's called alpha renaming. So in effect, all that's sorted out by the renamer. So if there are two different Fs, they get two different uniques, okay? And that's all the renamer does, really. That's its principal goal, is to transform rudder names to names. And then the type checker gets hold of the abstract syntax, type checks the whole of this very big data type, and replaces all the names with IDs. So an ID is, to a first approximation, a name together with a type. Right? So instead of F, we now have F of type int. And those names with type things, the IDs, appear both at binding sites and at the current sites. So, which may seem a bit redundant, because now you've got F of type int at the binding site, and every occurrence of F also says F of type int. But of course, they're all just pointers to the same value of type ID, so it's very convenient to play it that way. Yeah.
So is the renamer actually associating each identifier with its binding instance and assigning them all the same unique?
Oh yes, yes. So if if you mean if you see lambda f and then you sort of and I say f plus m dot f, and I've imported f from m here. Right. Is this legible? That? Yep. Yeah, good. So the renamer will say, oh, this is f. This m dot f here that I've imported in this import. This guy imported f. Let's call it f77. But this is f94, right? And the renamer will go and say, oh, this is f94, and this is f77. Right? Yeah. So in effect, every binding occurrence contains the unique or identity of its binder. Yeah. And furthermore, in the output of the renamer, there's no shadowing either, so that you can be sure that that there really is a unique place.
What does RDR stand for?
Reader. RDR. Yes, stands for reader.
Reader.
It
Okay.
could be parser. Yes. I'm going to tell you more about what Buddha name looks like, because in fact, a way to understand GHC is really the best way to understand is to understand its data types. Actually, understanding the code is the easy bit. The data types are the bit that you get real leverage. I think so. Quite a good implication of why types are so important. It's not just they keep your program consistent; they help you to think about it. Okay. While I'm here, let me just remark that, that yes, the type checker transforms the program to HsSyn parameterized by ID, but it also generates a type environment that that binds that contains the definitions for type constructors and classes declared in the program. So the type checker also generates things of type tycon and datacon and class, all of which we collectively call entities, and which we'll talk about a bit in a second. Okay. So, going back then to the big HsSyn type that we were looking at before, I promised to tell you a bit about its peculiarities while we're going by. So remember that HsSyn is both pre-type checker and post-type checker. Quite a lot of information gets added to HsSyn just by making those names into IDs, because IDs have types inside them. But that isn't all the places that we need types attached to the tree. So one way in which we attach types to the tree is by having two different constructors for, one way in which we attach type to the tree is by having type annotations in the abstract syntax tree that are simply invalid before the type checker. So here you'll see HsExpr has a constructor called explicit list. And explicit list corresponds to the production in Haskell when you say square brackets. When you write in Haskell square brackets A, B, right, this square bracket notation is an explicit list. That abstract syntax is maintained in full glory. And this post TC type field here is simply bottom before the type checker. So in the output of the parser and the output of the renamer, it's just bottom. So in fact, it's bound to something called placeholder type. And placeholder type is a call to panic. Panic is a useful function that's defined in compiler utils panic. It says, so you call panic if something has gone wrong, right? The compiler is wrong. That's the one that outputs the thing that says, this is probably a bug in GHC, please tell us. You've probably, I'm afraid, seen some of those very well. So placeholder type is just a call to panic, and you'll see lots of places in HsUtils, for example, we build fragments of this abstract syntax with placeholder type for these post-TC types, and then after the type checker, or the type checker, builds an HsSyn with these post-TC types filled with real types, because a post-TC type it's just a type synonym for type. Okay? So there's no static check that after the type checker it's filled in and before it isn't. We could have added an extra type parameter to HsSyn to make that static, but we didn't. That would be quite a cool thing to do. It could be unit before, or void or something, and type afterwards. But we haven't at the moment. Yeah, that'd be quite nice. Little exercise. Project. Add it to the project page. Yeah. It's always nice to have projects that are pretty mindless, right, that you can just crank through. So that's one way in which type annotations get added to the tree, but it's not the only way. So there's a few cases in which the type checker takes one constructor in and produces a different constructor out. So constructor patterns are a good example. So on the way in, when the parser, when it sees a constructor pattern like you write f of some constructor A, B. So this thing here is a constructor pattern. And on the way in, it'll be a concat in. Oh, what's this located of ID? So located is defined in basic types source lock, src, loc, and it's GHC's mechanism for adding source locations in the parse tree. I haven't got this in the write-up, I might as well mention it now. So how is it? It's declared like this: data located of A is L of, and then there's a source span and an A. So it's simply a pair. Located of A is simply a pair of a span that describes the range of characters which this thing lives in on the screen. And the value itself. So here, located of ID. ID is the type over which HsSyn is parameterized. Just says this is the constructor. So here, the span for this one will just go from here to here. And the HsCom details tells you about this part.
Where does there live a map that tells me how a character position associates to a file line and column?
Right, so source span, look at, so this is good, you can look at the source code. So this guy is defined in basic types. Basic types is a good place to look for data types that seem to be somewhat pervasive across the compiler. And this one, if you think it would be in source span, but it's in source lock, just I think. So source spans contain the file name and the line number and the character position, all of the above. So in a little black water. So it'll tell you that. We should say something about source span somewhere. Yeah. Does that make sense? Yeah.
This is for the post type checker type.
Yes.
I'm still trying to wrap my head around that. You say that the parser fills the post type checker field with an error tag and the renamer does not touch it.
So the renamer is building renamer takes a HsSyn tree and produces a fresh one, right? So it's not, this is all functional programming, right? So, and so sometimes the renamer, I forget whether the renamer, it's probably a bit user idiosyncratic. Sometimes you might, as it were, match on the incoming one and just put it unchanged in the outgoing one. Sometimes you might just say, right, placeholder type again in the outgoing one. It doesn't make any difference. But so long as the renamer doesn't look at it, what the renamer really mustn't do is look at that post TC type, because you'll just get a panic if it does. Make sense?
And you do that rather than having a maybe post TC type.
Yes, yes. So maybe would mean maybe would give you a so why would that help? Is the trouble.
Well, you could check whether it's there without panicking.
Yes,
but
you know whether it's there.
Trees where you'd have parts of it with types in it, parts of it without, which is, like if you think about the
it's quite nice. You'd have to un-maybe it.
Yeah,
all the
but
time.
it would also be more expensive to do that because
then you get
have
extra
to
maybe
keep
nodes
changing
that.
things. Yes.
Yes.
I think the answer is that the nothing case will mostly be panic. So we're just
Yes.
So it's always the right thing to do with panic if you see enough.
Shortcut the panic. Yeah.
So there is one bad thing about it being an error flag, which is that the pretty printer for HsSyn, sadly, so this would be an improvement if we parameterized over it, wouldn't it? Yes, right. So at the moment, the pretty printer can't ever print these because the pretty printer doesn't know whether it's doing an HsSyn of ruler name or HsSyn of ID, right? It just pretty prints. So at the moment, the pretty printer never prints these post-DC things in case you're pretty printing. The pretty printing is just for debugging output, right?
You could make them of type ID just as well too, and have them maybe in the cases where you need it, and then.
You can make this of type ID, you mean?
Yeah, and just have that.
Well, you could, but oftentimes there is no ID. There's no variable.
Right, you have to have the maybe with
It'd be a bit of a fake.
some of the ID types.
But it'd be better just to parameterize. Parameterize HsSyn with respect to the post-DC type. That's a good idea. But then the pretty printer would know. Good. Okay. So moving back to this, sometimes there are a few cases in which you'll see something in and something out, and that means the parser and the renamer generate this guy, and the type checker generates this more heavily decorated guy. I don't want to go into the details of his decoration just yet, but that's what you should understand. I think that nomenclature is followed consistently. And then the third way in which you may see constructors appearing in HsSyn that you may not easily make sense of is that there are some constructors added by the type checker that have no apparent connection to the underlying abstract syntax. It's not just there's an in and an out, it's completely new. So this HsCoerce constructor in the HsExport type is such an example, and absbinds in the HsBinds type, the binding group, is another example. So these are invariably to do with stuff to do with type abstraction and application. So in JT's intermediate language, it's very explicitly typed System F style, and Haskell is implicitly typed and doesn't have explicit type abstractions and applications. So we have to add them somewhere. The type checker adds them by way of adding these extra constructors. Okay.
Is it safe to say that's sort of inferred information?
This is, well, yes, it may be, yes, it's inferred information, right. So in principle, at the moment, I would like to be able to say that you could take a typed program and convert back to the original untyped program simply by converting the IDs back to rudder names or to names, and dropping all of these guys and moving from the outs to the ins. And to a first approximation, that's true. I've never tried it, and I'm sure that something in detail will go wrong, but that's the idea. Yes? Yeah, so evidence abstraction application for type classes, where you're saying, so we're saying that the intermediate language has type abstraction application. It also has evidence abstraction application, so you typically end up, when the Haskell programmer wrote lambda x dot something, by the time it gets to the middle of the compiler, it will look like lambda alpha lambda d with type num alpha lambda x with type alpha something, right? And this part is type abstraction. This is what IVAS is calling evidence abstraction. And so yes, those also show up in here. In fact, it's done by the HsCoerce.
So it uses the normal function. It's not the separate.
No, it's inside HsCoerce. It's not done with HsLam. So this guy here will be in HsLam because it corresponds to what the programmer wrote, right? And this part here is going to be. I remember that I forgot to tell you something. The GOT at the moment is in the process of having its wheels removed while travelling at 70 miles an hour on the motorway and replaced. GOT's intermediate language used to be essentially System F, and now it's become System FC, which I'll say a little bit more about in a second. One of the changes that I made in doing this change was to tidy up this particular guy. This guy used to be, if you're looking in the head, you will see tyap and tylam, I think, as constructors in HsSyn. If you look in HsExport, you'll look for tyap, tylam, and dictap, I think. I think that those are all still in the head. But what I thought, for the purposes of looking at the insides of GHC, the sensible thing to do is to tell you about the compiler as it will be like tomorrow, because we have all this FC stuff is done on a branch, and so that's what I'm going to do. If you want to see the differences are not too great, so you don't have to look at the FC stuff. But if you do want to look at it, it's in the Haskell.org darks repository. So it's darks.haskell.org. So you might want to do this just to get hold of, just so you can browse the code. And then it's GHCFC2. That's the repository that has the latest, greatest Haskell compiler. And this will become the head very, very shortly. We decided not to make it the head before today because that was kind of destabilizing and changing. We didn't want to accidentally screw up the entire hackathon by doing this, but this is a place to look.
Is that a minus or a hyphen?
It's a hyphen. Oh, a minus or hyphen?
No, and that's right.
We don't have Unicode for names, so you really see that. This is a hyphen or minus sign, but not an underscore. Good. Right. Now this to do say more is because, in fact, if you're going to understand just exactly what these constructors do, you have to say a bit more about FC and type abstraction and so forth, which I'm not going to do right now. But this is it's one of the things which later on today you might want to know more about. Okay, so at the moment you can see the strategy, and I'm looking at these data types sort of one at a time in a bit more detail, because I think if you understand the data types, you're a long way ahead. But I'm sort of guided by you. You can ask lots of questions, or if you just look, if you're happy to move on, we'll move on to cast HsSyn. Yeah.
So let me ask a question about type parameters. I assume that this ID parameter is fairly pervasive.
It's the parameter with respect to that HsSyn is abstracted with respect to. Yeah.
So if you were to add another parameter for, say, the post TC type,
good.
How far-reaching a change is this?
So if you add an extra type parameter for the post TC type, which is just what I'm suggesting would be a good thing to do, then you'd have to change all the types in the HsSyn module, but you'd have to change very little else, because you'd probably make a type synonym for
common instantiation.
For common instantiation. So we often say type, TC HsSyn is HS expert applied to ID. Now the HS expert applied to ID and type. So you might need to go and, in order to limit the number of changes, you might need to go and adding some more of those type parameters. But that's the place it's really good having a type check language, right? Because you can make a change like that, and you can be pretty confident that it may be tedious, but you can get it right and you won't break anything.
I don't believe a word that says any change requires changing 40,000.
There's something very restful about doing mindless changes. I really like that. Because
I agree.
Got a lot of jets here, and you have to work. You have to make your brain work so hard. But just doing something like adding a type parameter to everything. Think, oh, good, I'll do that now.
It's great work for plane flights.
What was that?
It's good work for plane flights.
Yeah. Actually, a good strategy is often change it in one place and start compiling, right, and then fixing typo messages. You only have to make one change, and the type checker will force you to propagate that everywhere.
So this would be a good point to talk about your guys' roadmap for the template Haskell syntax versus the Haskell syntax.
Oh, let's get back to template Haskell. Yes. So in principle, you might think that template Haskell would be this would be the data type for template Haskell, but it isn't at the moment. It's a completely different data type for that. So we should, I'm trying not to get into that just yet. There is about the implementation stuff about template Haskell. There isn't, but there should be. It'd be a good sub-page, the sort of implementation of template Haskell stuff. Yes. Okay, so much then for HsSyn in all its glory. So here we are. Right, so the next thing I want to do is to say a bit more about rudder names, and these entities, these ID things. Okay, because again, this is all still front-end stuff, but it's understanding the data types is the keys to the kingdom. So the rudder name type is really important. I said to a first approximation it was just a string, but like many things in GHC, the things that to a first approximation are just a string actually have 4 constructors and use 3 other data types in the world. So here they are. So here are rudder names, and they're defined in this module, compiler basic types rudder name.lhs. Many of these types are fairly well abstracted, so rudder name is a good example of an abstract data type. Its representation is known only to rudder name. Oh, did I lie? I'm not sure. I think so. You can check whether it's truly abstract. So, a rudder name is the thing that the parser parses. So, and the parser can parse names in 2 forms. One is an unqualified name like x, and another is a qualified name like m.x. So that's what these 2 constructors, qual and unqual. This is what the parser sees in source code.
What's an octave?
Right, so what's an octave? Why don't we just have string here? Well, it's because in Haskell you could have the data constructor C and the class C. And these are not the same thing. Right? Now the parser knows, even doing parsing, which of these 2 things it's looking at. It knows whether it's parsing a type or data constructor. So right at the very front, as soon as it's parsed, we'll attach to the string something that says which namespace it comes from. So op names are defined in this same, well, the op type, yeah, in the same file. So an op name is, as I said, more or less just a string, but it has a namespace as well. So here it is, namespace and string. Ah. Well, not quite string. Let's do with namespace, because that's the easy bit. So namespace really is a data type, right, with 4 constructors and no interesting structure. And then the namespaces are variables. So this includes data constructors, and so the variables that you write, the term level variables you write in your source program. Type variables that you write in types. Type and class constructors, so that's the capital ones, because Haskell has the same namespace for type constructors and class constructors, or type constructors and classes, I should say. And then there's one other slightly strange thing, which is data, the data namespace, that I'll have a bit more to say about data constructors in a second. But the ones that appear in your source program, when you write capital D as an occurrence, it's one of these bar names. Okay? So that's the namespace. Now, what about this encoded LS thing? Why isn't it just a string? Is it still like this? Is it still encoded?
Yeah.
We still keep them encoded.
That's just a synonym for fast string.
Right. So
it's not encoded.
It's not encoded anymore.
That's right.
It used to be encoded. We better, if it's not encoded anymore, we better change the name. Yeah, I copied this out of the source code. So this little debate is saying, well, when we print out labels for C compilers, we can't put in %%, which is a perfectly good Haskell operator. You can't put %% as the name of a C function. So when printing them out, or even in assembly code, so when feeding them into subsequent tools, we Z encode these names. So %% will be something like ZDZD or something. So it's just a simple escape convention. The encoding is described in this ocname file. And what Simon and I were discussing is, in an ocname, do we actually store it in encoded form or non-encoded form? And we forgot.
It's the original form.
It's the original form, right? So it's stored as a fast string, which is a compact form string. In Haskell, a string is a list of characters, which is rather a spacious representation. Inside GHC, there's a data type called fast string, not currently described anywhere here, which is not only compactly represented, but also shared. So all copies of a single fast string are shared, right?
That's right, they support order 1 calls.
Right, and when you compare fast strings, it's an order 1 test, not a run down the list test. So maybe this should just say fast string.
It does.
It does in the source. It's a record with 2 selectors.
You were looking at the wrong source?
No, I was looking at the wrong source, right. So maybe you could go, somebody could go fix this then. Can I press refresh?
Hands up if you're fixing it.
Good. Yes, we need a consensus mechanism for.
Encoding injectors. We have a function named ZP.
Oh yes, yeah, no. If you have a function called ZP, that will go to ZP or something. Okay. No, that's right. So you won't get. No, that would be bad. Yeah. No, it works. That's right.
Now the Z encoding process on a fast string is level-based as well. So if you try and Z encode the same fast string multiple times, it won't happen once.
So is fast string like stored in a central table, like symbols?
Yeah.
Yes, so they're shared. There's a sort of, essentially there's a shared hash table behind the scenes. Okay, so that's ocnames. Now, and so now we've dealt with these. Oh, we almost have. What's a module name? So a module name is something like M or yes,
Step back for a moment. Tell us, why are things this way?
Well, so why are ocnames this way? Because that's the way Haskell was designed.
I have a bit of intuition about that. I think it's you could have an ocname be just a string. Why do we attach its namespace? And the answer is because sometimes you need to build mappings from ocnames to things, and you might want to have both classes and variables and other things in that mapping. And if you didn't have the namespace attached, then you have to build separate mappings for separate namespaces. And it's very convenient to have the namespace attached.
Yeah, that's good. Write that down. Yeah, right. So then in fact, the awk name, in the awk name module, you'll see a data type called awkn, which is an environment whose domain is awk names. And so it's very helpful that you don't get mixed up between the data constructor and the type constructor when you're building such things. Did that answer enough? Yes, that was the particular point. Good. So a module name here, module name is also just a string, except then it goes m.s, so it may have dots in it, but that's not disaggregated in module name. Module name is just fast string, I think. In fact, there's a little bit of documentation about that here. So module names are defined in module.lhs, and for some reason package configure. Strangely, that's what package ID is. That's what package ID. So I've copied some declarations here. So module name is just a fast string, but we use the new type here. We use new types quite a lot, so that we don't get one kind of fast string mixed up with another kind of fast string. Right? That's a convenient paradigm, you've seen. So module name looks like this, and a module. Oh, I haven't got to module yet. That's just module name. Oops. So you ready so far for qual and unqual? So those are the ones that are read by the parser. Now, sometimes it turns out to be very convenient for a rudder name to also be able to say more exactly what it is. So these guys get their meaning from what's currently in scope. Right? So X doesn't mean anything. You have to say what's in scope. These guys do mean something. So a ridge says this awk name from this module, and here we mean not just the module that's in scope, but this particular uniquely defined module. And this furthermore must be the module where this guy is actually defined. Unlike here, for a qualifying thing, if you say m.f in your Haskell program, module m must be imported, but f might not have been defined in module f. F might have been defined in module k, and m imported it and re-exported it. Right? So in this qual form, this module name is not necessarily the name of module where the thing that is ultimately referred to is actually defined. That's what we call the original name, or the original identity of a value, is the module where it's defined and the occurrence name where it's defined. Does that make sense? Because that's an important distinction. You're familiar with the idea that if you say m.f in your Haskell program, then f might not be defined in module f. Is that all right? Okay, good. So, but in the ridge case, it must be defined in this module. This is saying, this is exactly where it is. This is like a unique identity for the thing. And modules are, so this is now an extension to ordinary Haskell. A module is a pair of a module name and a package ID. So this is new as of a month or so ago. We finally bit the bullet and made this idea of packages into a properly supported thing in GHC. So a module M in package P is a distinct module than module M in package Q. Right? And the package ID distinguishes them. So a module is is as it were like the original name of the module. It has real identity, whereas a module name is just a string. And there's one of them in here, and of course there's also one of them in those qual things. Yes.
If these rudder names are being generated by the parser,
yes.
Does that mean that the parser can't possibly be knowing where
Good.
these things are coming from?
So how does the parser generate these? He would never generate. Does the parser ever generate any of these?
Yeah.
Well, now I'm struggling to remember exactly where these ridge things end up being generated. I know. Here's an example. In the deriving mechanism, well, when you say data blah 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 deriving stuff, what does GHC do? It generates some Haskell source code, right? But the Haskell source code it generates must not just get the names that are currently in scope, right? It wants, if it's saying, I'm expecting to see the prelude map, it wants to say the map that comes from GHC base, not the map that's currently in scope. Okay, so that's a good example of where you want a ridge stuff. So it's very convenient to have this possibility. user written code never gets converted into these two. It's just sort of more internal mechanisms that do.
Would that be a use for packages then? You'd have the base packages, prelude, map, and a different.
No, it wouldn't help, right? Because if you generated a qual for like this qual thing, just says, you know, module m, right? And that's whatever m is. If you say import m, you better say import m. There's no way to say in Haskell source code, you know, package m this module, this entity. That's what a ridge does.
It comes from the GHCI input parser too?
This a ridge stuff?
Yeah, if you give a module name without, is that a different layer?
No, in GHCI, if you write in a GHCI program a module m.f, you'll get one of these, but it's resolved when it's parsing user source in the same way as it is if you wrote it in a module.
You mean the command prompt in GHC?
Yeah.
Where you say, where you refer to a qualified name, isn't it scope?
Yeah.
I think that then turns into a rig.
Isn't it scope? Oh, maybe yes. Yes.
I think we go and read the interface file for the module you say explicitly, and then we turn it into a rig.
If I just enter the wrong, I wrote down what Simon said, and I want to get it wrong. Refresh it. Tell me that.
Oh, I love this. Where did you write it down?
Right there at the bottom.
Oh, yeah. When we want to say use prelude.match down. Yes.
User written code. Down.
Oh. It never gets translated. I think. Well,
Is that true?
yes. I mean, if you say deriving blurb, right, then it's the stuff that's generated from the deriving user written code. Well, right. It might be good to give the deriving as an example of when we do generate a ridge, because it's a classic example. It's really makes it much easier to deal with.
This is a classic macro problem, right? You write a macro, you generate some name, and you want to know where does that name
go
in
scope. Template
where the
macro
macro is
generate
defined or where the macro is expanded, and that's exactly what's going on.
Right. In effect, this allows you to say to the renamer, don't go looking for what's in the scope. I know what I want to talk about here. No. There's no way to say that in Haskell source code. So click. Yeah. Now this third form is a kind of more efficient variant of a ridge. It's where we not only, where when you're generating this stuff, you not only know exactly which module, which op name it is, but you even know the unique. Right? You know everything about this name. Right? And then you can just say exact. And that's, I think this B is probably a lie. Because I think this is out of date. Out of date, yes. Remove B. Look at it.
Removing.
Maybe can somebody just remove B? This is actually it better be removed from the source code as well. This is just a copy of the source code. This B is historical. And template Haskell does this, yes. It does generate.
Done. Removed.
Oh, removed. Excellent. Ah.
You probably have to log into the network. No. Yay.
You've got to submit a docs patch as well. It's got to be removed from the source code. That really was literally copied from rudder name. Thank you.
From rudder name.
Yeah. Okay. So that's rudder name. And so to a first approximation, you don't need to worry too much about these, but it's very helpful to know that they're there and what their semantics is. Their semantics is here the renamer goes and finds what name corresponds to this module op name pair, and here it just says, use this name. If you want to see where they're generated, that's what's okay.
Maybe we should say ghc.base.map rather than prelude.map.
Yes, that ghc.base.map would be better, because in fact, there is a module called Prelude, but it's a module that imports a whole lot of library files and exports them all. So in fact, it would be a mistake to say prelude.map, because that isn't the module where map's declared. It's in fact, I think, ghc.base, isn't it? So that would be yes. This is right in spirit, but wrong in detail. Yeah. Okay, so much for rudder names. Is there something? Right, so that's rudder names. So the next thing is names. So the renamer is changing those rudder names into names. So what's in a name? So here's what a name is. So a name is just a record of 4 things. It's got its awk name, which really is the same awk name you'll be relieved to hear, the same data type and the same awk name as was in the original runner name. The bang says it's a strict field, yes. That makes it more efficiently represented. The unique here says this is the identity of the name. It's a unique number that makes it fast comparison. Its source location is the place where it is bound, where the name is bound. So that's useful just for error messages. It's only used for error messages. So it's somewhat optional. This and the name sort tells you more about the name. And so the name sort is the main interest in bangs up. And they get lovely. Lonely. Oh, I see.
I don't think it helps with the bang on the part.
Oh, on the name sort. Oh, yes.
What is the hash sign?
Oh, int hash. This is another non-standard GHC extension. Int hash means an unboxed integer. How does it spell bang in? Since that was half the same thing. I can't remember. So it's an unboxed integer, meaning an honest-to-goodness 32-bit bit pattern, no nonsense about thunks or laziness. Right. So GHC has this extra. It's a new primitive data type, not in Haskell, but in GHC.
We don't want to unpack the output. Unpacking the output into the name is bad.
But we do want to. So we have per field unpacks. Right. So that all the interesting action in names is in this name sort field, and it's really very helpful to have some mental model of what this name sort stuff is going on, because names pervade the entire compiler from the renamer right through to the back end. So it's worth knowing about. So there are 4 constructors in name sort, and here they are. External, wired in, internal, and system. So internal and system are the simple ones because they're really just saying I'm a locally generated name. I'm a name defined in the module being compiled. Sort of purely local, just within a single module. And the only difference between internal and system, maybe it should be a Boolean modifier instead. The only difference between internal and system is that system says, well, this was kind of made up by the compiler. Like type variables are all called T, the internally generated type variables. And so it's not very helpful to print their names. Right? Whereas if you've got an internal one, this started life as a variable that was defined by the user, like f or some local parameter or function. So it's worth printing that. So it's a pretty much a difference in error message generation. And sometimes in unifying in the type checker, if you're unifying 2 type variables, one of which has an internal name and one has a system name, it would be better to eliminate the system one in favor of the internal one rather than vice versa. So these 2 are pretty simple. External is a lot more fun. So an external name is a globally unique module occurrence name pair. So you'll see that the external name contains a module here, and it's got its awk name in the rest of the name. So that module name awk name pair is what I was earlier calling an original name. Those are the fields in the orig rudder name, right? So this uniquely defines the thing, and so for every particular module awk name pair, there's a uniquely defined unique that gives its identity.
Is that awk name always going to be in a ridge for the external case?
Awk names, rudder names that have a ridge, ridges, right? Awk names were just the strings with the namespace part. Yeah. So no, it's keeping this taxonomy separately. That's partly why I'm emphasizing the data types so much, is because once you've got that taxonomy in your head, it's much easier to navigate the compiler.
What about the packages? Did you say module identifier?
Modules, remember, I said modules are not module names. Right, so a module is a pair of a package ID and a module name. And those are the things that are in name sort. So the distinction between modules and module names is really quite important as you'll is essentially implying here. So it is indeed a module here and not a module there. Okay. So I don't want to say very much about this maybe part because actually we're Simon and I were just talking yesterday about trying to eliminate it. What this when you have a data type declaration, you define a type constructor with a bunch of data constructors. And the data constructors kind of belong to the type constructor. We call the type constructor the parent. So the names for the data constructors would contain just type constructor name as a here. So it's a way of getting from the children, the subparts of a declaration back to the name of the declaration that encloses them. But it's a little tricky to keep this all consistent, and so we may or may not stick with that. So that's the intent.
Is it only data types?
No, it's also classes and class operations. Essentially anything which belongs to some larger declaration unit. Record fields, yes, same thing.
What about local function names?
Wait, what?
Local function names.
No, no. So a local function, a local function definition in the body of a larger function definition does not have the outer function definition as its parent. No.
It's not an external name.
Could you define it by like whether you can use the parentheses after the parent in the module export list?
Oh, yes, for the user visible ones, it's exactly those. So in an export list, you say T open brackets ABC, right? And those are the things whose parents are the enclosing T. Yes. But there are some things that we'll come across where you've got names for things that that are not explicitly named in your Haskell source at all. Right. Oh, lunch in 15 minutes, good. Right. Right. Okay, so there's an example here. I think that's all we need to say about external names. And wired-in names are the last sort. And we've been through endless variations of doing wired-in stuff. There's a whole page about wired-in stuff. A certain amount of what GHC, a certain amount of what you might think would be in a library is known to GHC. For example, GHC knows internally what the Boolean data type is like, right? Because, for example, in a guard for an equation, it's important that the type of the guard is bool. How does it know what bool is? Well, bool is kind of baked in. We say it's wired into the compiler. But bool is also defined in a library so that we generate the code for the data constructors. So these wired-in things are both defined in libraries and defined in the compiler itself. Also known somehow to the compiler itself. So wired-in things have names that just like an external name, have which module it's defined in and its parent, but also they have this tie thing. And the tie thing is a type constructor, class, identifier, or data constructor. It's the fully type-checked, baked-in thing. Right? So this is just as a Buddha name. It's a bit like an exact Buddha name. Do you remember an exact Buddha name says, don't mess about, I know what my name is. So a wired-in name says, don't mess about type checking me. I know what type thing, what the type checker stage is going to generate for me. Right? And so that's built into the name here, this type thing. This built-in syntax flag is a very simple flag that just says whether this wired-in thing is supported by built-in syntax. There's very few of these. It's things like open square bracket, close square bracket is for dill. And you can't rebind that. And so you don't want to bring it into scope or out of scope. So just occasionally we need to know when something's built-in syntax. All built-in syntax are wired-in things. So we don't need to know any other types. Okay? So there's a few more details about that are given, I think, in here.
Is that a monad's done in the same way? There's bins.
Yes. So, so where am I going to? Let's see what we do have. Let me. Where is my stuff about why? So since we're on this digression, let's suit the action to the word and dive down the rabbit hole. So this page, which is on that main list of contents for GHC deals with, tries to describe the sort of mental furniture you need to understand when you're thinking about what does GHC know in a baked-in kind of way. And it turns out there are actually 3 different kinds of baked-in things that GHC knows about, depending on how much it knows. So the wired-in things it knows everything about. The known key things it knows they're unique and they're which module they're defined in. And the original names it just knows which module they're defined in. And each subsection of this page says a bit more about those things. So I think I'm mainly going to leave you to read this, though of course I'll be happy to return to this. The wired-in things are mainly type constructors. Like bool is my classic example. You can see the compiler really needs to know about. And it's very convenient. You can just refer to it as a top-level declaration. So in ties wired in, you will see a declaration of bool tycon. It's a top-level declaration of something of type tycon, and that is the type constructor for booleans. And so it's completely wired in. But bool, of course, also has a definition in one of the prelude modules, GHC.base, I think. But there are other wired-in things that don't have definitions in the library, namely primitive types. So primitive types are ones that cannot be defined in Haskell. So they are only baked into the compiler, and they don't have Haskell definitions in anything. But they also count as wired-in. And you'll find the definitions of those in ties prim. All this sort of baked-in stuff is in compiler prelude. Ties prim for the primitive data types that can't be defined in Haskell. Ties wired-in for the data types that can be defined in Haskell but are also known to the compiler. And it's completely undefined what will happen if ties wired in has one definition for bool and GHC.base, the library module, has a different definition. You'll be deeply stuffed if you do that. Okay? And there's an example here of the bool tycon worked out. Now, sometimes GHC doesn't need to know everything about it, doesn't need to know the tycon, but it's very helpful to know it's unique, right? So that you can, and it's defining module and ocname. This is, a good example of this is when we're generating derived code, I think. Or when you're, when you write a dot dot, in square brackets a dot dot in Haskell, then you're by implication making a reference to a class called enum, right? So you've got to know about the enum class. Now it's tedious to make the enum class be wired in the sense I previously described, because the enum class is fairly elaborate. So, but the typechecker on the other hand has access to environments up the wazoo. So it's okay to look up the enum class in the environment. And rather than look up a rudder name, we say, oh, we'll just fix a unique for the enum class. We'll say ghc.base.enum has unique 72. And that's defined in prel names. And then we can just look up that name in the type environment. So in effect, when the type checker wants to know about the enum class, it looks up that name in the environment. We could go one stage further back and look up a rudder name in the renamer's environment, and then look up the resulting name in the type environment, but that would be a two-stage process, and it's easier to do it in one. So there's a bunch of known key things. There's quite a lot of these, and they're all mostly defined in prel names. Yeah?
So these are elements of Haskell syntax that is hardwired to a particular library?
Yes, that's right. Where the typing rule, like the typing rule for square brackets a dot dot, if you look at the typing rule, you'll see it mentions the class enum. Right, it's not explicit in the source code, but in order to type check it, you must look at the class enum. Or
it is fixed to being in a particular module. So if you move the enum after another module, you have to change this the name. And that's the price we pay for having a name rather than a rudder name.
Well, yes, even a big difficulty with the rudder name, like an exact rudder name would still say, sorry, a ridge rudder name would still say which module it's in. Yeah. I couldn't move it. So, yeah.
So if you want to write new syntax that references particular libraries, for example, that you have written,
right,
you would just add them.
Yes. So if you want to add some new syntactic construct that it refers in an implied way rather than an explicit user-written way, it refers in an implied way to some data types or classes or identifiers that you've defined, you would use this same mechanism. Yes. So that's why it's worth understanding, is because it's yeah, because otherwise it can be difficult to know where to plug in. Lunch is here, so we should just finish this up. So, I frequently find myself wondering, and where do all these known key names show up? Well, how did they get into the compiler's environment? So I've written down for you the place that it's done. You can see that we initialize the name cache is the guy maintained by the renamer that maps module occurrence name pairs to names with their unique. And we initialize the name cache from this bunch of known key names. And the known key names are all the wired in things and all these basic known key names. So these are the ones that are not wired in, but where we nevertheless wish to establish a unique for them. Okay? And finally, there's a bunch of things which we do refer to without a unique. We just go one stage further back. We don't give a unique, but we do say, we do give an original name for. So again, they have definitions that are usually named something like name underscore RDR, capitals, and they're all defined in kernel names as well. And these are ones used by, a lot of them used by the deriving code. It's tedious. Doing this is a bit easier to extend because you don't need to allocate a unique. All of these essentially have their uniques allocated by hand. You'll see a big table in the kernel names. It's not very sophisticated mechanism. So it's a bit easier to add a new one of these than a new one of these, but then you have to look it up in the renames.
I'm still kind of wondering why you need this unique. You seem to use it to implement shadowing.
In here, well, so why do we need the unique? It's because if you want to get at the equality class, you do somehow want to get the equality class, not the equality class that's in scope, but the equality class defined in, GHC.eq or something.
Okay, but why wouldn't you then just refer it to its original module name?
So you could use this, you could indeed use this, use an original name. Yes, you could, that would be fine. Then you would, to get all the way to the class object itself, the class value itself, you would first have to look up this original name in the renamer's environment. The renamer's environment is the bit that maps from one to the other, and then you would need to, then what would you need to do? Then you look it up in the type environment. So this just removes one lookup. That's all. So you could get rid of known key names, this middle category, by using exclusively this guy. And I don't think you'd lose very much. Yeah. So part of it's historical. If we're starting again, maybe I'd only have these. All right. So I guess we should stop for lunch, since lunch seems to have arrived.